for me to get a cluster running in EC2 fairly directly, and I'm going to make it available on the ICME website. I'm going to pass it around right now for people who want it. It's a directory called EC2 scripts, and just copy, it's like 5 files and just copy it.
You said it's on the ICME site as well?
It will be. I have to run by there and hand it to them. Okay, so after much screwing around, I spent about 4 hours finding a data set that made sense. I grabbed this, which is 80 years of NOAA weather. So it's US, I don't know if there's Alaska or Canada in there. US weather data. It's 139 million rows, 20 gigabytes on disk. It includes year, month, day, the station in some weird encrypted way, min, max, mean temperatures over the course of the day, sustained wind, gusting winds, humidity, dew point, rain and snowfall, other flags for special things like thunder and tornadoes and whatever else. The data is in an Amazon S3 bucket, so you have to have an Amazon account, and you should be able to find the bucket, Stanford-cme250A. I've used the same bucket all semester long. Under a directory called weather, and then I put the scripts within that directory, and below that there's a data folder, and it's got 89 files for, well, 89 years of weather data. So there's a couple different ways to do this project. This one is take the weather data and do something, well, look for evidence of global warming and also be able to predict temperature for a given day and station. And that will be what the test will be, is I will run through a set of stations and days that your model hasn't seen and get your predictions out, and then confirm that you're more or less on track with what you claim the model is supposed to be able to do. So there's no goodness metric about how good the model has to be. The question is really, how did you build the model? Why did you build the model the way you did? What's supposed to be the expected level or quality of predictions? And can you report that to me? Right? So I'll talk more about that in a second. And then for the global warming prediction piece, this is just simply use your powers of observation. It's not necessarily machine learning, but it's definitely data exploration on big data. And try to figure out how you would look for evidence of global warming and can you find it. And so, for instance, the obvious thing to do is just take all the temperatures across all stations and average them all and per year and say, what's the trend line? Okay, well, Alaska is colder than Texas, and so you'll get different temperatures at different places. Are there more stations in Texas than in Alaska? Well, stations get added over time. In the 1929, when the data starts, there's far fewer stations than there are in 2016. So if more stations get added in the continental US and fewer in Alaska, then that's going to skew your numbers. So you can't just take an average across all stations all years and hope to get something reasonable out. Same thing for seasonality, winter versus summer. You have to figure something out there. So talk to me about what you did and why you do it. And that is the part of getting a pass here. The other option is to do a big join between the flight data, which I used in a prior class, and the weather data. They're both in the same S3 bucket. And then do a giant join and do predictions, just like I did in class, where I took the flight data and I built a predictive model. I built a couple different predictive models, okay, and I made a prediction. I could make predictions based on where you're coming, where you're going, and what day. Now add weather data and try again, and see if you can't beat the model I built in class, a couple classes ago. In particular, tonight I'm flying from SFO to Chicago. What are the odds my flight's delayed? What airline should I use? What is the least failing airline that does fly from SFO to Chicago? Right? Okay, I'm doing the same flight in a week. So what's the prediction next week? How about Thanksgiving? I didn't do any holiday predictions on my data set, but Thanksgiving really screws with flights. So maybe figure out how to add a predictor value that says I'm true on Thanksgiving and false elsewhere, or maybe it's true on Christmas and Thanksgiving and false elsewhere. And then rerun the model and ask the question, what are the odds of getting flight delayed on Thanksgiving? So in both of these, what I want to see is you expressing to me how to repeat your work. So you're doing data science, you're doing some kind of science. I have to reproduce your work. And in fact, if you go out in the real world and somebody asks you to go do this kind of predictive modeling, what they want is not a mathematical thing that lives on your laptop. They want to take that predictive ability, put it into some business use case, typically some sort of production environment, and have somebody else make predictions on a regular, steady basis. Right? So you have to be able to teach somebody else. So if you're busy building a model and you have some domain expertise and some modeling expertise, maybe you don't have how to go run an IT ops cluster reliably 24/7. You know, Google Maps gives me time and distance calculations and a bunch of options and includes like traffic. Some clever data scientist or team built that model, but that's a very different set of people from people who actually productionalize it so a million people can go ask that question every day. Right? And so the difference here is you have to be able to teach the other set of guys how the hell your model works. So that's why I want to know how it works. You have to teach me. So some discussion on how to run your script and get answers is sort of mechanical. Hey, I ran Python. Here's my Python script. I pointed at this cluster, and I just hit Python space my script, and it does something. Then a discussion on what you did for the data munging choices and why. There's no right or wrong answer. The wrong answer is I didn't do anything, or I'm not going to tell you what I did. The right answer is say, well, I threw out the following dead columns, and I had to do a join on time, but the time stamps were all wrong, so I had to go hack the time columns this way, and that's it. It's like a paragraph. And then a discussion on the model fit and quality, and I'll talk a little bit more about the metrics here. Mean squared error is a common metric, and every model will produce it. What is mean squared error? If you're in the stats, this is like old hat, and if you're not, maybe it's new. It's simply, I have a slide. Here we go. I'm building supervised models here. I have the right answers. So if I have the right answer and I have a prediction for my model, I can see the difference between the two. How close to right am I on every single prediction I run? And that difference is an error. If I square it, it's always positive. I'm going to add them all up and average them. That's the mean squared error. It's a common metric for goodness of fit. Another one is R squared. And it has a couple different meanings, a couple different domains, but the easy one here is simply on a scale from 0 to 1, how good are you compared to just predicting the average? Right? I'm looking at the average temperature across the US for 90 years. Can you do better than that? You should be able to do better than that, if nothing else, by predicting using the station location, because Alaska is simply colder than Texas, and that's, the mean is somewhere in the middle. So how good are you compared to just doing the mean? And that will be also reported by these models in the metrics in various places. For logical or Boolean predictions, am I delayed or not delayed? You get a true and a false. It's yes or it's no. You have cancer, it's not. It's fraud, it's not. So generally the models actually produce a probability from 0 to 1. Where, closer to 1, more likely it's cancer. Closer to 0, more likely it's not. And so you get a threshold where you want to say above this, I'm going to declare it fraud, and below this, I'm not. You get a range of thresholds. You get a choice of thresholds. And now becomes an interesting question. What is the cost of a wrong answer? So if you blow a prediction on my flight to Chicago, I'm annoyed. But that's it. Whereas if you blow a prediction on cancer detection, some guy doesn't go in for the next set of invasive tests and waits a year before cancer gets discovered. It's a serious health problem. So the cost is different, right? The actual penalty for being wrong. So what you want to do is look at what are the different choices I get if I choose different thresholds from 0 to 1. As my threshold gets closer to 1, I declare most things not true. And as it goes towards 0, most things are true. And then, what is the usefulness of having it true or not true? So here on the picture there, I'm showing a sample AUC curve, and it's showing there's a false positive rate running from 0 to 1 at the bottom and a true positive rate running 0 to 1 at the top. And what it really means is that as I raise my threshold, I get a series of curves showing where I'm going to say you're in, you're out. And the area under that curve is a metric on how good my model is. Because if that area includes the entire square, then all thresholds are fine. My answers are always correct. The model is 100% accurate. And as the line gets closer and closer to the diagonal, it's a die roll. 50-50, doesn't matter what I pick for my threshold, 50-50 right or wrong. I'm not actually predicting with a damn. And so you want to know what the area under the curve is and what that AUC curve looks like, and all these modeling techniques will, the dual logistic or prediction, a Boolean prediction will report that. So pull it out and display it. A higher AUC means your model is more accurate, however you want to choose the threshold. And where you choose the threshold is a domain-specific issue, depending on what you're trying, what is it that you're trying to predict. Back up here, I zoomed past. So some easy mistakes to avoid in this project. Predicting based on information you don't have. So, for instance, predicting flight delay tonight based on whether the flight's canceled. Well, the flight cancel won't happen until later anyhow. So you can't make a prediction right now. And next week as well. So if, tonight you run home and you get all happy and go at it big time and you solve it all, you make a prediction for next week. If your prediction includes flight cancel delay for next week, you don't have that data. You can't make that prediction. So you have to build a model that doesn't do that. Same for predicting temperature next year. Is it global warming? Okay, what's the average San Francisco temperature next year? How is Stanford University temperature next year? Okay, you're going to use the dew point. It's highly correlated to the temperature, but you don't have dew point next year, so don't use it. Right? So figure out how you're going to make that choice. And then no test train split, because that leads to overfitting that you don't know about. Tell me what you did, and I have been having email discussions with people who are just now getting bugs in the system. Just now getting H2O turned on and installed. Now's the time to do it. There's 2 weeks left for the semester. You may find you're spending hours and hours and hours just like suffering through basic install problems. Get that figured out as fast as you can. So I'll be busy and responsive to email as best I can, and so talk to your neighbors as well.
So you don't need explanation of the data munging aspect?
No, that is a mistake to avoid.
Oh, yeah, so you actually need a coder to
Tell me, give me a paragraph of what you did and why. Yeah. I'm not expecting a giant write-up. Yeah, I'm just expecting something simple, but nothing is wrong. Okay, so the data's on AWS. I've put the slide up several times. You should be able to have already gotten an AWS account, however you get it. There's this freebie account. So far, in my hours and hours of exploration, I've run up about $25 worth of chump change on my AWS freebie account. Shouldn't be a problem doing the assignment here. The launch scripts, people came in late. I handed out a splash stick. Has a directory, some launch scripts. I'm going to talk about them here right now. I'm going to put them on the ICME website, but you can get them right now. Wherever the flash, who's got the flash stick? It's halfway through the class. Okay, so pick up a copy of the flash stick there. You'll need Python to run those scripts. You'll need a Python package called Boto, which you can do pip install Boto on most machines that will just up and install just fine. You'll need to get this one. There's several scripts in there. You'll need to pick up, give me a second here. I have some bug that's just loving me here. You need to hack this one file. The file has a pretty clear discussion about where you need to hack what pieces. The comments are pretty heavy in there. Read through the comments and look. You'll need an AWS access key and the secret part of it. You get that from logging into AWS and asking for one. And they'll hand you both halves, and then they'll throw one half away, and you'll have to copy both halves, save it in a text file somewhere, hack it into this file. You'll need an SSH key pair name and the private half. Same thing, go to AWS, follow the tutorial, get an SSH key pair name. The key pair name has to appear in the file, as well as a link to the file which contains the private bits. The private bits are about a paragraph of random garbled text. You'll need a security group with the right set of ports open, TCP, UDP ports. There's a discussion in the file of what that looks like. If you can't figure it out, talk to me. It's going to be basically open the range of ports that we talked about earlier in class. If you just open all ports everywhere, and you're just doing a homework problem, so maybe your system gets hacked, but it's a homework problem, so maybe you just reboot and try again. You can open everything, it would work. Pick your number of instances and the size. I went with 4 instances of 32 gigs. So it's probably overkill for this project. The data, counting everything, will probably actually run on one fat node if you don't want to mess with the cluster, but you might want some more cores, I don't know. You run it by calling it out in Python, and I'm going to demo here in a minute. And theory says, 2 minutes after you run it, you have a cluster up and going. And you can connect to it with Python and with Flow, and I'm going to do both today, and load the data and go. So once it's up and you connect it with Flow, I had a 4-node cluster this morning, so these are all from this morning. I'm going to try again here in a minute. You see this is 4 nodes. You see this is 32 cores from 4x8, 100 gigs of RAM free. So 20 gig data set, that's substantially more than I needed for this. Should be fine. I went to Flow, I hit import files, I had to mess with, so S3N is I'm talking to S3 file path. Stanford cme250A, that's the bucket. And then weather/data, and eventually it comes up, says 89 files. Let's say parse it, take the setup, by default parse, 2.5 minutes later, I can view, and I get this. That's 139 million rows by 31 columns, and data. Year, month, day, temp, dew point, sea level, station, pressure, runs on and on for 30 columns. So just some fun things to look at here. There's a lot of 99.99999s. If you go get the NOAA weather data description file, I'll tell you they're using that to mean missing value. So step number 1 for doing with the weather data, you should figure out how you're going to turn all these guys to missing values. Because like the mean temperature, the mean dew point is averaging 9999 and minus 126. And it's a garbage number, right? So you can't ask for the mean dew point or the mean temperature here until you can do this cleanup. I'm going to do it in Python, make your poison, how you want to do it. The magical 9999s vary from column to column, so you'll have to figure that out as you go. It's not all the same. And no, I'm not handing you my script, although you can probably figure out and copy it from slides, I don't know. But you should be able to figure it out from there. Okay, so let's see if I can make this go now. So first thing I do, I've logged into EC2, so this is click here. I'm going to refresh this to make sure my Wi-Fi is working. Yeah, it says I have a key pair. That's my SSH key pair. I have a security group. The one of interest here I've called H2O. I'll look at here. It has, you can't hardly see it. It has rules for open port ranges. I've talked about these in class. 8443 I added because it was like wget, but I don't think you need it. You want SSH if you're going to SSH into the instance. And all icon lets you ping it, but that's not necessary otherwise. Dashboard. I have no running instances right now. I also went to the S3 buckets here, and I've been able to find my Stanford S3 bucket. Includes all years. That's the airline data. And there's a weather data, and here are 89 files ranging from a few megabytes to hundreds of megabytes, half a gigabyte, and there's a lot, so you get about 20 gigs of data there. And the last file actually has the headers, and the parser will just take them all in one shot. So given with that, let's see if I can do this thing here. I'm going to launch my Python instance script because I've already hacked it. In fact, I'll show you I have my keys buried in the script. Not too late. So I've taken this script. This is what I just passed out. It's got my secret keys in it. Aren't you happy? I'll delete it at the end of the semester, I guess. And it's got the access key, the secret keys are both like garbage things I got from Amazon when I asked for one. Here's my file, which just has a copy of the SSH key. Here's the name of the SSH key, click cme250 test key. Okay, security group H2O. I wanted 4 instances of M4 2x large. You can go on the Amazon site, launch an instance, and see a choice of instances you want. I didn't touch any other flags, and everything else is just the same. And it's in the middle of claiming I've launched, and he's going to try and upload a jar file for H2O. Back over here, we're going to go to running instances. I'm going to see I have 4 instances currently running. So my script is in the middle of its 1-minute wait, and then it's going to start poking them all and see that they're all alive and well, and then it's going to upload files to them and launch H2O cluster on them. Knock on plastic. Did not resolve host name. That's very exciting. EC2 52 that is a correct host name. Yes. Oh, all right. Status says initializing still. So for whatever reason, EC2 today, of all days, is being very, very slow. So in a minute, I'm going to time out here. So the status check says initializing. It actually means the 4 virtual boxes are up and they're being booted. The OS is booting. In the past, it's always been reliably done in under a minute. So I might end up timing out here and having to rerun the sanity check if you're up and alive and doing something. Nope, he claims he was able to log in. They're still going. Oh wow, he's gonna let me go. All right, he's doing something. Okay, he's got one of them, got an H2O instance up and running. See if he's still reporting anything different on the website yet. No, he still claims he's getting there, but it's gonna go. O3. Da-da-da. Okay, something happened here. So, I'm going to grab public IP from one of these instances. It likes to rewrite them. Come back here and do it again. And plug it in with port 54321. And see what we get here. We get a lot of nonsense. 60, yes. Yes. No. Way up here. We can also do it by. This is the one I ended up connecting to. We can do it by that name as well. If he's not going to go. Hello, Stanford Wi-Fi. Don't tell me now. Okay. Maybe it goes, maybe it doesn't. And maybe... no. Okay, so status checks now say, 2 of 2. That's the... By the end time of those are done, that's you should be up and available. Okay, I'm not getting through. Let's see if I can do this. I can ping it. Okay. Yes, okay, hang on. Let me try another one here. No. I'll put that. Oh, this is going to be a real short class. This isn't good. Pick a different one. I'm pretty sure I do not have to end the flow. Yeah, you can't.
Those
can't
instances
connect.
already have H2O on them?
Yes, so that was part of the boot here. So what I did, what the script does, is it launches with an AMI. An AMI is an instance of a virtual machine. And the AMI, in this case, has a bunch of files pre-installed on it, including the latest H2O jar file. And this conversation that went on through here was the prefix of H2O booting up on each of the 4 machines. So it did something useful on each of the 4 machines, and I just don't know what. since I can ping them, but I can't log into Flow, I'm going to assume that something failed with startup on the machines. I'm going to have to go log in and diagnose. So let me. That's going to really suck here. So let's. All right, so where do we go from here? The plan was to go through the demo for about 45 minutes, and it's not going to go easily. So I can fight through the demo, and you can watch what it means to do this game. Or I can answer questions. Why don't we just do both? Here, I'm going to fight through the demo, and I'm going to take questions, but there's no demo right now because it's all toast. I'm going to log into these machines.
What's the problem?
Well, exactly. No, but seriously, that is exactly the issue. What is the problem? And so I can't find the connector to Flow. Yes, why'd you not do that? Yeah. No, SSH. Now you're doing it. That's exciting. Sigma too. Okay, bang. So I've logged in, and okay. So I'm claiming this is something to do with Amazon. He has logged in and made a cloud of size 4, and this is up and running. There's nothing in the error file, so it's all good. This is Amazon not letting my cluster be visible from the outside. So they're supposed to make this public IP, public. And then exactly, well, that's the funny thing. Okay, come back here. What did I do here? I did ping. So I can ping public IP, and yeah, he's listening on the port, and he can't use the private IP address. What did I do last time that this was working? I had it all going this morning. He should be on the public address here. We can try the private one, but my recollection is it's not the one that's going to work. Because that's an internal IP address. And the ports are the same. And I am missing some stupid step here. Okay, let's go for round 2. This is tunneling, and I'm not supposed to need tunneling to the public port, but let's try it anyhow. Okay. All right, I had a tunnel. And I didn't have to this morning. I don't know what happened. That was Amazon not making the security open enough somehow. Okay, but I'm in. So let's see if it's otherwise connected here. Okay, so as soon as I get Stanford 250A, I get the auto completion starting to show up. And let me see here. Nope, I don't want that. I want this. Okay, fine. So I'm going to add all. I got 89 files. Way down here, I'm going to import. Okay, so now we're off and away. So this is mapping the 89 years of weather data into the H2O cluster memory. Roll down the bottom, parse. That's going to look at the prefix of each file and do a parse or guess of how to load the entire 20 gigs in. So it's now, this is actually loading data from S3. There it goes. Way down here. Okay, here's my parser guess, which is comma separated, and I built this CSV file, so I know they're fine, but it took me a couple hours to do it. And here's a prefix of the first few rows from things. We hit the parse button here, and it's gonna take off here in maybe a couple minutes. And we'll have something happening. Okay, so now it's loading data. So this took about 2.5 minutes last time. I know from practice that if you do a lot of the data import steps, it gets faster because S3 caches. But and that would be the case if you were, for instance, doing this from Python and you were rerunning and testing a script to get a workflow that was reliable. So can I answer any questions about the project here or expectations? People, who here has not yet attempted to get H2O installed? No one's going to admit to it? Okay, so far there have been several issues. I recommend you get after it. Okay, who here has taken H2O and loaded one of the datasets in and messed around for a little while? Gotten to the point where you can build a model. Okay, so that's most people. All right, fine. Who here is actually...
Can I ask a question?
Yeah.
The thing I didn't totally understand how to do in H2O is the data munging part, like how to...
Yeah.
Because what I did it outside because I used a smaller data set, like
Okay.
mechanics, so I
Right.
could do it in R.
Okay.
But I don't know how to see like even a graph with that giant data set. I don't know if you do it within H2O, I don't really know.
Right. So I'm going to do it with a combination of Flow and Python.
Okay.
So I'm going to pull up Python, and I'm going to do data munging in Python. And the R workflow is very similar. There's a little bit of syntax changes because it's R syntax instead of Python syntax, but it's roughly the same idea. I'm going to leave this cluster up. I'm going to start up a Python process. I'm going to attach to the cluster from the Python process with H2O in it, where I put that IP address that's supposed to be public, and I'm going to try the public one first. If that fails, I'm going to use my tunnel one. Once I've connected to it, I'm going to give Python a name for the data set in the cluster. And then I'll have in Python what looks like an R data frame, except it's backed by the cluster. And then I can do things by column name, by row number and column number. I can add and subtract columns. I can get means and averages. I can do...
Can you show how to open this Python process here?
Yeah, I'll do it in a second. I'm going to wait till the data loads.
Oh,
And then we'll look at the data in Flow. And what I do in Flow is Flow has minimal graphing capabilities, but I don't know how to use Python's graphing capabilities. So if you're familiar with R's graphing capabilities, you can use it for data sets that you pull over from H2O to R, but you'll have to sample on the way. So you can ask for, give me okay, I've got a column, 159 million instances of it, I want to see some sort of plot on it. So I'm going to sample it by 1%.
so is that what you're suggesting to do?
That's what I'm suggesting to do.
So not Python, sampling it?
No, to do a graphical view
Yeah.
of something that's not in the Flow's basic graphical summaries, to pull it local to your box and do your graphing tool you're comfortable with. And pull it local, you have to sample by down to 1%. And that's because we don't have a giant heavyweight graphing capabilities in H2O.
And that's what you meant by data munging for the product.
For the data munging, I do simple numerical summaries, and then I do scripting, you'll see here in a second, where I am changing data sets. Like here, like I was showing on the slide earlier, I've got station, that's like Weather Bureau, Army, Navy, year 1929 to 2016. Month day is this funny behavior. 1/1 is January 1st. December 31st. So if you want month and day to do a join on the airline data, you'll have to break those fields out by dividing by 100 and taking a floor. Right? So here's temperature. Yeah, that looks kind of sane. I don't know where the hell minus 118 degrees is. That sounds kind of scary. But max dew point is 99999, and I know that's wrong. In fact, the description says, hey, you have to go do something about it. So I can go get you so you look at the mean here. So here's the mean for the dew point. It's 532, but it's averaging in a bunch of 9999s. So that makes no sense. You can't look at the roll-ups this way. You have to go do the data munging for any other things make sense here. Same for like wind gust speed. I don't know what the max gust is, but there's a 9999 that obscures what the actual max value is, and what the mean value is, and so on and so forth. There's a couple other fields in here, including snow depth, precipitation. The report, you'll have to go get what the data set has these letters. I don't know what they mean. It's in the description file. It says something like, hey, it snowed today. Or not. It was cloudy, it was overcast, whatever. You can go find out what those mean. Go back to outline, go back to my frame summary. Tornado, true and false. Okay, there's no 999s here, but it says, since the mean is this, it says whatever, 1/5 of 1% of the days had a tornado, where 5% of the days had thunder. Okay, and hail was down to 1/3% of the days, something like that. Some places, overall, over everywhere, 10% of the days had snow. It might be snow on the ground as opposed to snow in the air, I don't know. And so on and so forth. Okay, from here, I'm going to go switch over to Python. So I'm going to launch my little Python IDE here. And I'm going to go find my Python project. Okay, so here's my little Python. He needs an init, which includes the public IP address. That was the one I used from this morning. So let me see if I can't get EC2 to be honest about it being public now. I don't know. So we will see if this works. And if it doesn't, I'll use the internal one. Yeah, I think we're in the middle of a timeout right now. Okay, so it's not going to work. It's going to time out. I'm going to wait for it to time out. And if it doesn't time out quick, I'll kill it and try again. I don't know what the stall length here is on this guy. All right. Okay. And then let's see what this does. It fails because I do that. Okay, so now I've connected with the tunnel version. Total free memory says 87 gigabytes. That's whatever is currently hanging around after loading in the 20 gig data set. And I'm going to skip my piece which loads a few small files. And I'm going to go down here and do oh yeah, I'm going to do this piece here. Okay, so now I'm going to do part of the connection. If you load it in Flow and you want to use it in R or Python, you need to get the name of the key that HO is using, which is x1929.hex, because I loaded files called x1929 is the first file I loaded. And then I think it's git data frame h2o dot. It's probably git as data. And if I can type here, oh, that one. did this before. What the hell did I do? I did this. I went over and said H2O Python docs. I went to the website and I said, okay, Python module, data manipulation, modeling. I see one here, yeah. Somewhere in here I said get data frame, no, get frame data. Frame ID. And it varies by whoever, so that's what I think. Okay. So what happened here? Oh, something piled out. Okay, so what did I get here? Okay, so somewhere up here I see piles and piles of columns and piles of data, and that was too many, so let me try again here. With just one column. Okay, so there's a station, it has numbers that are meaning to me. There's a max of 9999. Here's the temp summary. Okay, minimum temperature minus 108.5, max 110 degrees in the shade. That kind of sucks. There's a mean and so on and so forth.
Can I ask a question?
Yeah.
When you said this, the initializing thing, for Python and R?
Okay, so the initializing thing, so yeah, well, let's look at that real quick. It does vary, and it's going to vary from what I have in Python. I don't have an R version, but the R version is actually somewhat simpler to use because R has cran, and H2O has a package on cran.
Okay.
So you load the H2O package from cran pretty much straight up. You follow if you go to the H2O website and you download H2O for R, it's the same H2O jar file, but there's more instructions that basically say uninstall your last copy of H2O on R and install this one, which is basically, suck it in from cran. Then there's a beginner tutorial which says go do a H2O init on a cluster and away you go.
Beginner tutorials like H2O?
It's on H2O website. Yeah, there's some tutorials there. So what I have up here in Python, which is Python mode, import, get current directory change, all I'm doing there is setting up so that I can use the installed version of H2O Python module here, not from CRAN, and I have it on my engineering build and not on an official, stable release build, because I have a, H2O build going on in process here, right? So that all ends in import H2O, and the stuff above it is simply changing my working directory to go to my engineering build. Fine. Then the init will be the same as an R, except it won't be called H2O dot. Actually, it might be an R. I think it's called the same thing there.
It's H2O, I just...
Okay, and you'll have to put in, IP import, which is what I did up here in Python. Way up top here, I went and said H2O init local. So I used the tunnel version. That failed. I need the port number, so I tried again. Oop, go down the line here. Bam. There we go. Near the bottom, port 555 is what I tunnel to, and then I'm connected. So if you launch it locally, to explore locally, you can leave off the IP import. If you don't have an H2O local, the R and Python guy will both launch a local on your Lappy instance.
Okay.
And that'll work for playing around to explore. When you want to go for the big data, you have to launch in the cluster, and you have to tell what you're doing here, the R and Python. Here's where I put my cluster. Okay, so I have some data in here. And I'm going to do the basic cleanup here, which is, grab all these guys and screw around with data munging, and it's going to. So that's going on. Let's do this. Back to flow. I'm going to admin. I'm going to water meter. What's a water meter? Water meter is a perf bar. What's a perf bar? It's a bouncing ball. It's a bouncing thing where green means your CPUs are busy, and blue means they're idle, and red means they're waiting on idle. So this says the cluster's busy. So I have 4 nodes in the cluster, 8 cores each, and they ran and they're done.
What does that mean?
IO stalls. So what did that actually do? If I run over here, it ran a long time, and data. Let's look at precipitation here. I can spell precipitation or min temperature, max temperature. Oh, we looked at gust speed in the GUI and it was 9999. How about that one? Okay, so now my max for my gust speed is 135. Okay, so probably in the last 80 years somebody took a reading at the middle of a hurricane, I guess. But the mean is 24 for a peak gust per day. Somewhere in the day you had a 25-mile-an-hour wind gusting once. There's a lot of missing values. I don't know what that means. Gust speed was not reported much of the time. If I count my spaces in there, I can see I've got 117 million missing out of 139. So it wasn't reported all that often.
What was that? 0, 1, 2, 3 NaN?
Okay, so that's row number, and NaN means no data,
Right, that's
missing value.
Why?
This is the first 10 rows
Oh, that's it.
out of 139 million. So I'm missing some non-zero data. I can go find it. There's a which in both R and Python, which will tell you what rows have data that's not missing. Here I'm missing what looks like 117 million missing, so I probably have 20 million rows of Gus data out of everything. You know, visibility. I don't know where this one's. Let's do one that's probably more reported here. Max temp. Summary. Yeah, okay, this one's better. So max temperature is mostly reported. 180,000 missing out of 139 million. It's 1/10 of 1% or something. It's almost all there. Average max temperature on a day was 61 degrees, and so on and so forth. So I have some data. And then that's it. From here, what I actually did is I built, I'll just do it here. I built a logistic regression model. I have that file somewhere lying around. Yeah, let's do one here. Where's this one? This one's better. So I'm going to do data.names. I'm going to pull the names out of the columns I'm going to train on. I'm going to remove temp. What's the names? Oh, come on. Names dot. Do that right here. Yeah. Oh, it's a freaking function. Wrong name here. Yeah, fine. Oh, I see. Okay, so here's all the names without temp in them. That's fine. Okay. And we'll do this. Make a generalized linear estimator. Take the defaults. Train. The X names will be foo. The Y name is temp. The data set involved is frame is data. So I get that right. It's going to do something. Okay, my cores are all busy. Oh, they're coming and going. There they go again. So something's happening. I go back to my flow interface. I can go admin jobs. There was a parse job here. There's now currently a GLM job in progress. It's running. Watch it bounce around. So I'm doing generalized linear modeling. Standard Gaussian, not logistic. I'm trying to fit a continuous variable. Looks idle. Let's see what happens here. Bam, done. View. Okay, took no time at all. Okay, so here you go. So the model predicts using max and min temperature to predict the mean temperature. Ta-da. Seems pretty obvious. And furthermore, if I go down to my training metrics, pop open, here we go. I'm going to see mean squared error and R2. So mean squared error here, the square of the error across everybody hits 5.7. So the actual error is like 2.5 degrees, given the min and the max as your main predictors. And R squared of 0.99 is like heavily overfit. It's a superbly good fit. 99% of the variation of the data is totally explained by this model. So the model is excruciatingly accurate because, of course, it's busy using min and max temperature.
If my R squared is closer to 0, then also there's an insight?
Yes, it says that your model sucks.
So I'm not, let's say I'm explaining a variation in the data, 0%. That is also a great thing to know about two variables, right?
It's equivalent to predicting the mean value.
If I was 50%,
If you are, if your R squared is 0.5, then half of the variation is being explained by the model. That's actually a model that's doing something.
Okay.
But that's like usefully good.
Okay.
You can have a negative R squared, and that says your model is anti-predicting. And that you should.
R squared can be negative.
It can. If your model is worse than average, So the average value, suppose your average temperature is 65 degrees and you predict 65. Then you're predicting average and you get an R squared of 0. Suppose instead you pick 200 degrees. Okay, that's a lousy prediction. You'll have a negative R squared. You're not as good as the average. So you hope to get better than 0. You hope actually to get 0.5 or better. That says half the variation can be explained here.
Another quick question. In most of the projects that you've done, what is the R square value that you generally hit most of the time?
Okay, right. So that varies entirely by the domain.
Okay, I see.
So different places will have different levels of predictive quality, and then whether or not somebody pushes hard to get better depends entirely on what is the gain to be had by better prediction. So if the answer is I'm at a 50% R squared value on predicting cancer on people, the gain to raising that to 80% is some fraction of people don't die. So that's actually valuable, and so people want to try hard, right? If the answer is, the prediction technique is people like you want to see this movie on Netflix, the gain or the loss to Netflix as compared to the worldwide economy is pretty actually modest. Netflix cares that value goes up, but nobody else cares.
Right.
So their predictive value is probably running around 0.8, and they're trying to get it to 0.9. And that means that some interesting fraction of the time they show you movies that you actually don't want to see, right? And then what's the penalty? Well, you say fuck you, and you move on, right? You pick the next one, or it's not time to watch movie night, you go do something else. So it's not a huge penalty to society as a whole that Netflix gets it wrong. So maybe their model's not as accurate, and it's hard to predict on people. Some other things are very easy to predict on, and the value may be high or may be low, but it's easy to predict on, the value's high, you generally bet somebody's already making a pretty good job of predicting it. If it's hard enough that you need machine learning and the value's high, then there's a sweet spot there, and there's probably a business case, and if you jump on it for the next guy, then maybe you got a running business concern going there. You're building a better mousetrap. So actually, that's it. I loaded the project data and I predicted on temperature in a bad way. Yeah, go ahead. Yeah.
So why would you use the adjusted R squared instead of just using the normal R squared?
You mean what do you mean by adjusted R squared?
Right. There's a formula for it. It's another metric that they use. I think it thinks
Okay.
about like correlation between
Right.
terms.
So there's a lot of R squared correlation variations. What I'm presenting here and what I've mentioned on the slide is simply what I said, which is amount of variation explained by the model, by the null model or the trivial model, which I'm predicting the mean. You can have other modeling techniques for which predicting the mean makes no sense as a baseline starting point. And then you might want an R squared that's telling you how good you are versus some other baseline, or how good you are compared to known other features that everyone's just going to account for anyhow. You're trying to say how much better I am than what came before, and sort of the default easy thing is to what came before is I take the mean. But if there's some other things I'm going to account for, like everyone knows there's a large skewage in the data. I'm looking at average salaries in the U.S. Well, there's a giant skew factor, right? There's a huge number of poor people and a few very, very rich people, and you look at this crazy thing. So maybe you don't want to do the mean. That's a lousy initial prediction. No one would bother with that. I want to take the log of that, predict the mean. I want to predict the mode or the median. I'm doing something else. Now, my R squared is how much better am I at that? Right? Take the default predictor and do better.
I wasn't asking the question from a statistical perspective. I was really asking it from a big data perspective, because I believe that when we have so much data, R squared is actually going to touch like a really higher value no matter what.
No, it does not.
It does not?
No, it is divided by the number of observations.
And what about...
It's like mean squared error. The mean means that you divided by 139 million. You added 139 million errors and divided by 139 million. So those metrics are independent of the size of the data, which is one of the reasons they're very commonly used. People will use them on 150 row data sets and 150 million row data sets. So one of the common problems that people have hit with, I shouldn't say common, one of the interesting problems that got hit when big data started really showing up, if you look at the logistic regression packages of a decade ago, they had a lambda amount they would add to cause the problem to converge more reliably. That effect on the coefficients would squash them to 0. You would converge, but at a lousier answer. And you wanted to add some lambda to enforce convergence. Otherwise, the problem would never converge. You wouldn't get an answer at all. So you added some lambda term. How much lambda did you add? Some packages added lambda divided by the number of observations, and some did not. All right, and then if you did not add lambda divided by the number of observations, as your data set got bigger and bigger and bigger, your effective lambda got less and less. Your model got a more precise answer, which was blamed on having more data, but in fact your effective lambda was lower until you didn't converge. Your problem also took longer to converge because the lack of the lambda forced more and more and more iterations. It was very slowly creeping in on an answer. So one of the things we did in H2O is we sorted out which packages went which way, and our lambdas will divide by observations, so it's independent of the size of the data set. Yeah, but it was definitely like the default R package, GLM, I believe does not divide by the number of observations, but one of the other popular R packages for doing logistic regression does, and if you're looking at Iris, 150 rows, it's all the same. But if then you look at 1 million rows and then 100 million rows, suddenly things start to fall apart.
Right.
So we all ready to rush out and go do some machine learning now?
Or enjoy the sun.
Yeah.
So you said you made an AMI with H2O on it?
Yes.
Okay, is that accessible to everyone, or?
Yes. Oh, yeah, absolutely. It is. That is in that script. It's
Okay.
baked in the script already. It says go launch an instance using this AMI, and it has the H2O jar file built into it. Actually, if you log in, if you SSH in and look around, there's some basic data sets in there that you can load instead of the big data here. If my instances are still up, I have a directory called Datasets. And the Datasets is a big data directory. There's a small data directory. Big data has just the big data laptop, which is that big. And you can see a bunch of stuff in here, including the city bike data sets that I used when I did the bicycle round. There's a bunch of interesting testing cases. MNIST is a common character handwriting recognition data set. There's a bunch of popular data sets. So these are like useful if you want to just like, you're having trouble getting the data to load from the S3 bucket, or you don't want to deal with 20 gigabytes of data in the first cut. You can go to small data and you find Iris. And it's it's this little tiny 1 kilobyte data set, and you can load it up and see that it works. So that just gets you a sanity check instead of your sanity checking where it takes 2.5 minutes a pop to verify something happened. All right, where'd my stick end up?
Yeah.
So the last person has it? So everyone got what they want? I'll put it on the website, but take it today if you can. I don't know how long it takes to show up on the website. All right, see you next time. I think next time I'll try to do something more theoretical on